Hi everyone, this is the first video, so yeah, okay. So I will try to create some kind of series, I guess, from now on to actually kind of make a log of my journey, I guess, into being a researcher. And so for the first log, I will try to actually reproduce some papers or even try to reproduce the result of some research, right? And I will try to actually make this video just to uh, make a reminder for myself. I guess that's the first thing. And then secondly, I wanted you guys to actually know that research could also be fun if you actually wanted to try it, right? And so the thing that I will try to talk about in this video are mostly going to be like the progress of my reproducing research result, as well as the, I guess, some optimization or even some kind of adding something into the code base, right? So if also disclaimer, if there is something that I said wrong or even misleading, or it's not understandable or something like that, um, I'm sorry, because I'm actually trying to still study this kind of stuff. So if there's anything wrong with my explanation or even something like that, just tell me about it in the comment and I will maybe correct it or even try to edit the video later on. Okay, so for this video, for the first vlog, I will talk about the research paper that I've been interested in, which is this one. This is SymMC, Approximate Model Enumeration and Counting Using Symmetry Information for Alibi Specification. So in short, it basically, okay, so for context, right? So for context, for who you don't know what is actually SymMC and what is it actually for, right? This is all too gibberish for you who actually who doesn't understand all of this stuff. So I will talk to you about an SAT first. So let's start by searching an SAT. No, satisfiability is problems. Okay. Okay, so there is this formula, I guess, of problems, you could say. It's basically a problem of either formula can be true or not. So, okay, so here is in definition, a propositional logic formula, also called Boolean expression, is built from variables, operators, and conjunction, also denoted by this one, or the disjunction with this symbol, and not or negation, right? So there's only three operators that were used in this formula, and it will be okay. So yeah, okay, I'm trying to actually explain you from Wikipedia. If there is something wrong with this site, just tell me about it. But this is just like the simplified version of what is actually an SAT. When I talk about SAT problem, it's not SAT as in a test to actually enter a college. No, it's different kind of problem. So basically, if you look at this, right? So if you look at this, there's this list of, I guess, class, and each of these class will be connected by this AND, right? AND operator. And so basically, all of this thing will like, okay, let's pull out. Let's pull out some paint here. Yeah, I'll use click instead. Okay, so for context, let's say you have a formula like this, right? A, A or B, and then there is N, C, yeah, let's say C or minus B or negation B, right? So let's say we have a formula like this, and we want to actually make sure is this actually satisfiable or not. So in short, if this formula is satisfiable, it must be true. So all of this must be true. Then if it's actually not true, default, if there is, let's say, okay, there's minus b and b here, right? So let's say we plug in for the, there is going to be a, b, and then c. There's going to be 3 variables here, and each of these variable will have a value to them, right? So let's say for a, I will say it's going to be false, and b going to be false as well, and then c going to be true. So basically, if I were to say this, right, then this one will be so false or false, then this will be false basically, and this one will be true. Okay, so this is not satisfiable, right? So this is going to be false. Why? Because this is an AND operator, right? So okay, this is not satisfiable. Okay, let's try to find the satisfiable one, shall we? So the way we actually find satisfiable one, there is an algorithm called, I think, CDCL. Okay, so yeah, the conflict driven close running. So it's basically this. Yes, so this is like the way you actually this is just one algorithm. I think this is one of the algorithm that were used if you are to actually want to finish this kind of stuff, right? We want to know if it's actually able to be true or not. So the end goal here is to actually make sure, is it actually satisfiable or unsatisfiable? If we use all the combination of this, right? So all the combination of this variable, let's say this is true, false, false, or even any other combination that we might come up later on, and there is no single true value over here, then it is unsatisfiable. But if there is one, it only needs one, it doesn't need like two, then it is actually satisfiable, right? So it's only that. The only, so it's basically like this, right? This is the whole things of satisfiability problems. This is just a simplified version of it. There's a lot of terms that you might want to actually learn more about, but for now I will just talk about this in a simplified way to actually shorten the time, I guess. Okay, let's go back to the first topic, I guess. I'll check my recording first. Okay, so it's recording, just wanted to make sure. Okay, so over here on this paper, it basically said, okay, so there is this thing called symmetry breaking. So what is symmetry breaking? So it is a useful approach for pruning the search space to efficiently check the satisfiability. So it's basically saying that symmetry breaking is a kind of an algorithm, I guess, to prune, to actually, you know, let's say there is this problem, right? And there is a variable or redundant variable, I guess, that are way too many of them, but it doesn't really matter, or it's used rarely, right? We can actually, you know, just remove it. It basically is just pruning all the stuff, right? So it's basically what symmetry breaking is. As the backend solver of Alloy, CodeCode does, so there is this thing called CodeCode, which is a backend solver for Alloy. What is Alloy? Alloy is basically let's just say it's a language, right? It's not a language, it's some kind of a structural things that you can test on. It's either for software verification, security, or even synthesis, right? So that's part of symmetry breaking. So there's already a tools for it to actually do a partial. So it's only partial, it's not full, because in here it says, while full symmetry breaking remains challenging to scale, recent studies showed that CodeCode PSB could significantly reduce the model counting time. So for the full symmetry breakings, it's still challenging, right, for X to scale. But there is this for CodeCode, it could significantly reduce the model counting time, because I've tried the tools for this model counting and it actually quite take a long time. For example, one of the problems that I've actually tried on, it took around like 3 hours, I guess. So yeah, it took that amount of time to actually do this kind of calculation. So, however, the desired term is either the isomorphic count under non-symmetry breaking, which is there is no symmetry breaking at all, or it is a non-isomorphic model counts under full symmetry breaking. So, what is isomorphic and non-isomorphic? It's basically kind of like this. So, okay, so two graphs are considered non-isomorphic if they have different underlying structure, even if they have the same number of vertices and edge. So let's just say, okay, so let's see here. Okay, here, I guess this is the easiest one, right? So yeah, let's say there is this, right? There is 1, 2, 3, 4, 5. There's 5 edge here, like P1, P2, P3, P4, and so on. It's the same kind, but the structural stuff is different. For example, here, P4 on the graph 2 here, it will be connected only to P5 and then P3. While over here on the G1, there's 3 connection here, which is P1, P3, and P5. This is a non-isomorphic. So the isomorphic one is basically the reverse of that one. Okay, so if you look at this, right? So yeah, this might be look this might look like a different graph, right? Basically, but if you look at this, the connection between B and C is still the same, right? And then the connection between B and A is actually still the same. It just got like, for example, get turned around, or if it's good like that. But the most important thing here is I guess the connection in on it's between these edges, right? So we wanted vertices, I guess. So we want to make sure that all of the connection are actually still the same for the isomorphic. So that's actually the difference in short, what is isomorphic and non-isomorphic models. So as we can see here, it basically wanted to just either the isomorphic count, but without no symmetry breaking. So there is no symmetry breaking at all. Or we can use the non-isomorphic, which is the that doesn't actually have the different kind of connection, right? But also under full symmetry breaking. Okay, so basically this what paper says. So this paper represents an approach called SymMC, which utilizes the symmetry information to compute all the desired terms for all specification. To make SymMC scalable, we propose a approximate algorithm based on sampling to estimate the desired terms. We showed that our proposed symmetry have consistent and far-bound properties to our knowledge. SymMC is the first approach that automatically approximates non-isomorphic model enumeration counting for alloy specification. So it basically says that SymMC is the first approach that automatically approximates the non-isomorphic. So yeah, the non-isomorphic. So that this thing that needs to be underlined here. For model enumeration or counting for alloy specification. So it's basically for the non-isomorphic stuff, right? And so this is basically the whole summary of this paper. I won't talk about all of this paper because it might take a long time to actually talk about this one by one. So I'll just go straight to the research result, I think. So let's go to the code. Hold on a second. Okay. Okay, let's go to the code base that I've forked from the original GitHub repo. Okay, just another disclaimer. If there is anything that I said wrong, or even that are it's not actually true, just tell me in the comment and I will try to actually fix this stuff, because to be honest, I'm actually still learning as well. Okay, so okay, great. So we can see here, so this is the stuff that I've created. This is my own stuff, And beside these two, all of these are from the GitHub repo. You can actually check out the GitHub repository under the description later on after I upload this video. Okay, so for short, I will just talk about this. This is basically the whole code base, right? So there's going to be dataset, enhanced code, and then enumerator estimator. Okay, before I talk about this, I want to show you an image to actually simplify all of this code. Okay, so here is the image from the repository. So it basically have three step, right? So there is this thing, there is this tools called enhanced code. This is like the backend of the alloy itself. And so there's going to be an allospec. What is allospec? Allospec is actually a file that has an extension of EALS. Wait a minute. So okay, this is one of the example. Okay, so it's basically tell us that this is some kind of like, so this is signature book. It creates some kind of book, and then the book has like address and the name, and then for the name itself there is going to be a DDR. I don't know what is a DDR mean. It's probably an address. And then for there is going to be pred add if it's actually going to add a book, right? And then delete a book, or even look up the book, or del undas add. It's basically its own language of I guess, but it's more of a language of software verification or even software testing, right? So yeah, so it's basically like this, like it's a structured stuff that can be actually used. So you can actually run this on alloy. So okay, here is the app itself. There's actually a visualization of the structure of this stuff if you wanted to actually download the alloy analyzer. It's available on, okay, so it's okay. So if I were to actually put this on inside here, it will actually put out some, I guess, an error if I remember correctly. Okay. Okay. Okay, so it's basically there's nothing there. Wait a minute. Okay, so it's basically, yeah, wait, I'll look up some, hold on a minute. Alloy tools. Okay, so if you look at this, there is this, okay, documentation. Docs. Where is it? Alloy tools documentation. Okay, here, I think here it is. Formal FAQ comparison quick guide. Okay, I think it's quick guide. Or online tutorial. I forgot which one. Is it an LS? No, it's not that one. Wait a minute. Is it this one? Because I remember. Okay, so okay, right. This is the one. Yeah, the layout is different now. I'm kind of confused. Okay, so if we actually use, I'll just use this, right? So just to show you what it actually does. Okay, if we actually execute this and then show, okay, there will go, okay, it will show us what the structure of all this stuff is. Okay, I don't know why it's only those parts that are actually showing. It should be, okay, so it's basically, okay, so this is one of the stuff that we're going to be shown in the I guess alloy if you were to actually run it. So it's basically a structure of stuff. Like, let's say you want to try to build a hardware or even some kind of software, and you wanted to see if it's actually going to run smoothly without no fail, right? So we can use alloy as verification or testing. to basically see the structure and see if it's actually going to work, right? Or even see if it's actually satisfiable to our own requirement of software. Okay, so it's basically what alloy is, right? Okay, let's go back to here. So that's what alloy is. So the file is .ils, and this alloy specs will be goes into an enhanced code, and this enhanced code will extract this symmetry information, and after that it will goes into an SRT formula PSB. It's basically just converted it into some SRT formula, and after that it will go into the second step, which is all SRT model enumerator, and this will goes into model set, and after that this whole thing is the actually enhanced code, right? So this thing is different. This is the estimator. So what does the estimator do is basically just count the number of non-isomorphic or even the isomorphic counting, and it will output some kind of evaluation metrics and also the number of non-isomorphic model or set or count. For the isomorphic, it will count just the isomorphic without any evaluation metrics. So this is basically how it works in the graph or the visualization, I guess, right? And if you look at this code structure here, we can see there is going to be two folders here that are important. The first one is enhanced code, which is this part here, and then the second one is going to be here, which is enumerator estimator, and it's going to be here, right? Oh, sorry, from here. So this is enhanced code, and then this is the enumerator estimator, and it's basically going to run, right? So it runs, I guess it's on C++ if I remember correctly. Oh no, it's okay. The enhanced code it's in Java. Okay, so this one is on C, right? So both of these run on the different language. The enhanced code is on Java, while the enumerator estimator run on C. Both of these must be run one by one. So I was thinking maybe I might try to make some kind of an automation for the whole process, right? So I created two sh file that will run all the whole process for the enhanced code as well as the enumerator estimator. And for us to actually run off two of this stuff, we need to actually build them first, right? Because yeah, it hasn't been built. So the building is kind of easy, to be honest. You just need to install the OpenJDK 8 and then ENT for the enumerator estimator, and for the enhanced code you don't really need to actually install anything. Yeah, the OpenJDK one is probably for Java, of course. So the enhanced code you just need to actually run build as well as the enumerator estimator. You can just build you need to remember that to actually run this inside the folder, because if you don't run this inside the folder, it will the error will come out, of course. So that's the whole process of building. It's quite simple, right? And after building the code of this both to enhanced code and enumerator estimator, you can actually go directly into like using the SymMC. The first way is to actually, so there's only two steps to actually using SymMC. The first one is to basically translate the SCRT formula into the symmetry form information. The alloy specification into SRT, and then extracted the symmetry information. So it's basically the first step is just this, right? So it's going to extract the information and it will convert the L specs into the SRT formula, which is PSB here with partial breakings. And after that it will goes into here. So you run this code inside the enhanced code one, right? Yeah, you run this code in the enhanced code, or even you can just go dash enhanced code dash run.sh. Just run this inside the enhanced code one, and there's going to be three paths for this command. The first one is the spec file itself. So it's basically the specification of the alloy. If you look into the dataset, it's already being given by the author. On the specs there's going to be three, right? Yeah, there's going to be three: alloy, DS, and queens. But if you see here, there's going to be four. There should be four. The reason why there's only three is that the code one is written on a different language. So for the specs files on the code one, it doesn't return. But if you look at the sims, it's already being given. So okay, so if you look over to sorry, if you look over to this again, right? So the first one is spec file, and second one the SAT here. So basically, where do you want to put the SAT formula, right? It can be anywhere that you wanted as long as the folder existed. The second one is the third one is the symmetry here. So where do you want to actually put the symmetry information? Where to? The same as the SAT there, you need to actually need to make sure that the symmetry there already existed, because if it's not, then it will not be generated, or even an error will come out. So after you run this stuff, you can run one of these I guess command. The first one is to get the non-isomorphic model or count, and then the second one to get the isomorphic one. While for the third one, it's for the code pruning itself. Like if you want to actually uh, do pruning in the partial SVB, you can do a code pruning. You go to the path SAT file and then path to a sim file. So three of these command, you just need two of these, right? And then one flags. The flags, this is for code pruning, this is for non-symmetry breaking, and then this is for the full symmetry breaking, basically. So yeah, you can run one of these if you wanted to. So that's basically how you use the SymMC. But if you were to actually run this one by one on each of these, right, if you realize there's a lot of symmetry as well as the SAT file, right? So there's going to be a lot of this. For alloy, for example, there's going to be, yeah, there's a hell of a lot of this. If you want to run this, right, from just, let's say, one file, or even just, let's say alloy one, and then you can do this, but it will take a lot more time to actually run this one by one, especially if you're writing the code right here, right? I mean the command on the shell here. So I already created the automated test SH. It's basically just says to run this command, the enumerator estimator, as well as the enhanced code one. So it will run this first, right? So I get the first one is to run is the automate code. You can choose the directory, like for example, if I were to choose the specs one on the queens, you can go to the dataset CNSV and check for the sims file and then the SAT file. For the automate SI, you can also do this as well, right? If you want to do DS and or even do the queens one. Just make sure that you already written down this one. Like for example, if you want to use alloy, you just need to change this to alloy, and vice versa, right? Just change this one, the directory, or I guess path file, to the SAT or even symmetry information file. Just to make sure that you change those stuff. After that, you can run this, and let's just run this for example. I guess I'll do the automate. Wait, hold on a second, I need to cd. Okay, so okay, automate. Okay, so if we run automate discord, yes, okay, so it will run this, right? So it's basically it's running this one. Sorry, no, it's not this one. Okay, so it's running this one, and so echo running on name, it's running on bstx 10 node, and it's starting solving. It will quite take a while to actually finish this process, so I guess, I don't know, it probably depends on your system. I haven't tried it on other I guess local machine. I've only tried it on my own local machine. I haven't tried it on like VM or even the other computer or even lab comp. So yeah, it's basically like this. And then okay, it will take a long time, right? So and then after this, after you run both of these sh file, you will actually get the isomorphic or the non-isomorphic counting for these SAT problems, right? So for the sorry, not SAT problem, for the LI specification here. So for BST exactly 10 node, there will be the time and then the non-isomorphic or even isomorphic one. Okay, again, let's get move on to the next step, which is the research result, because we don't want to actually take long time to on this one waiting. Right, it took me around like 3 hours to actually just wait this stuff. Can you stop this? Okay, let's just kill the terminal. Okay, so it's basically like that. Okay, after I run this, this is the enhanced code 200. So after I run this, I realized that the total permutation, it takes quite a while, because the one of them is like 87 billion total permutation, which is quite a lot. And it took around like what is it? Let's this is on millisecond. Let's try to actually change this into an hour or something. Okay, and let's do hour. Okay, it took around like 1.4 hour for me to wait those stuff. It actually could take quite some times. Okay, so this is basically the result, and if you look at here, there is going to be 1 2 3, there's going to be 3, right? And then there is this SymMC. So this one is the other code, which is enhanced automate the test. For this one, there's some problems that I've encountered, which is, for example, here, I don't know if it's actually the problem of my own local machine or even the code base itself, but some of the stuff that meant to be shown are not shown. For example, here for the non-isomorphic model count, for the block and queen, it's shown 325, group scheduling 486, but sometimes it doesn't really actually count it, right? I don't know why, but it doesn't really. For example, here the n queen one and stuff like that, but it actually works for some stuff. And as you can see here, even there is, even for the isomorphic model, for the non-isomorphic model, it even reaches 1 2 3 4 5 190,000. That's quite a lot, to be honest. And also the time it took a while, like 910 seconds. This is on seconds, right? Yeah, this is on seconds. Yeah, as you can see, there's a lot of stuff here that took way too long. For example, here sorted list exactly 6 node. It takes around, what is this, 1 2 3, oh, this is 1000. It's not, this is not the number, this is a decimal point. So yeah, it took around 1665 seconds. Okay, so that's basically the result. So if you look at the graph, okay, so I already created the graph, and as you can see here, this is like basically the graph. So the blue one is symmetry extraction time, the total permutation, as well as the formula generation time. So as you can see here, there is like some missing stuff here, right? For the missing stuff that were shown here is basically because I don't know why, but when I try to run the code, there is some weird stuff like this. For example, here, if we look at this, right? Okay, so this is the one that actually do the weird thing here. Like there is this degeneration time. If it's actually total permutation, it's probably like, for example, a bit more makes sense, but this is like a time, right? So it's minus 241 times. It actually goes back in time. It's not going forward. It's probably something wrong with the time scaling or something, that it goes down to minus. But yeah, it's not really that big of a deal, to be honest, for this kind of stuff, because it's not that really much. You can okay, so okay, there's still okay, so there is non-isomorphic one for the address book one and the 3A as well. Okay, so that's basically it for the whole things of this paper. I've tried to read it, and you can actually try to read this paper also as well. The tools, I will provide the link on the description, but if you want the tools, you can see here, there's the link here, or even you can just see the description later on. For the paper, you can just search like this title. You can search on the Google. It will show on the first page, I guess. This is from the SEM one, or you can just go to the Wenxi Wang page here. One of the professor that are working on this paper. But I guess that's all for this video. If you like this kind of stuff that I talk about, a little bit of research that I've trying to reproduce and stuff like that, just tell me in the comment. This video is just meant for a log, so if there is any explanation that I've said wrong, or even it's not accurate, or it's not like accurate thing to say, something like that, just tell me in the comment and I will try to correct it. And because I'm still actually trying to understand this paper as well, there's some stuff that I still don't understand, to be honest, and I'm still trying to understand the actuality of this research. But for the next vlog, I will talk about the other paper as well. Probably I will talk about from the same professor. I don't know, but I will try to do some more a bit of variety of stuff in this kind of stuff. But yeah, that's all I guess from me. Thank you for watching, I guess. See you guys again on the next vlog.